Now, a number is written in scientific notation when it has the form a times 10 to the b power, where a is a number between 1 and 10, and b is an integer. This is a very common definition that you'll find in a textbook. But one of the things I wanted to point out is that to be in scientific notation, the number in front always must be between 1 and 10, meaning it's got to be like 3.2, 5.7, a single digit in the whole place, and then a power of 10. So like, for example, we looked at a few on the previous slide, but if I was trying to figure out where do I place the decimal place to try to move it from current location to before, you always want to place it between the first and second non-zero digit from left to right. So the decimal place would have to go between the first two numbers to properly be in scientific notation, because the number out front must end up between 1 and 10. So that would leave me with 4.2 times 10 to the 7th. And again, it would be times 10 to the 7th because there's 7 spaces in between there. And same with this one, I would put the decimal place between the 4 and the 2. That would leave me with 1, 2, 3, 4, 5, 6 spaces, which is why in scientific notation, it'd be the -6. And obviously when we're writing numbers, it can kind of look weird the way I did it here, but we always drop the zeros because zeros in front of the number or zeros at the end of the number are always not. You could write them, but we typically don't, because again, it just looks weird. There's more zeros. They don't really mean anything when they're in the front or before the whole number or at the end beyond the decimal place. So one other thing I wanted to point out is, like, say for example, I was thinking about the number 21,700. The question on the slides asks, well, which one of these is in proper scientific notation? Obviously the first one is not, but if you're looking at the next 4, they're all written as something times 10 to the something. And that's the essence of scientific notation, but technically there's a unique answer for scientific notation, which is the last. And all of these, if you really think about them, these are all the same thing. These are all equivalent ways of writing that original number. But only one of them is in scientific notation, and that's the one where the decimal place is in the correct spot. Now, technically, there is some merit to writing the number in either this form or this form, because again, this would read as 21.7 thousands, because 10 to the third is just thousands, and that's exactly what this is, 21,000. But because this would be in proper scientific notation, these all would not. But there is some value to writing them this way too, and it's just a way we define scientific notation. You know, it has to be in that range, but is it that important for the context of actually doing math? No, not really. So anyways, let's actually practice a few from the packet. So in the packet, we have a few examples. It says the speed of light is approximately 300 million meters per second. And oh, you can't see what I have. My bad, I had the wrong screen there for a second. It says the speed of light is approximately 300 million meters per second. And this is something where if you've never really had physics before, basically light, in our experience, light seems to be something instantaneous. Like when you turn on the lights, bam, we see the lights are on. When you turn them off, they're off. But technically, light is not something which happens instantaneously. It actually moves at a particular speed. The light waves, it just happens so fast that we can't really tell. And the reason how we know that light is not infinite, it doesn't happen instantly, is because things that are really, really, really far apart, there's a little bit of a time aspect for the speed at which light travels. And a lot of other signals and things, like for example, internet, or like in Wi-Fi and satellite sound waves, they all have various speeds at which they travel. They are not instantaneous either. Where it seems like, you know, when we connect our computer to the router, that connection seems instantaneous. It's not happening instantly. There's always time components to those sorts of waves. But light specifically moves at approximately this speed. It's really, really fast because 300 million meters, a meter is about, you know, it's pretty big. If it does 300 million is a whole lot of them. But anyways, you know, when we're trying to do calculations involving light, you know, say for example, we want to know how long does it take from the light of the sun to get to Earth. When we're dealing with larger and larger distances, those things matter. Whereas if we're dealing with, you know, the light, you know, in my room turning on, Well, it moves so dang fast I can't even tell that it actually took some time to get there. Anyways, but if I was to write in scientific notation, again, I would want to place the decimal place one space after the first non-zero digit. So this would be 3.0 times 10, and that is 1, 2, 3, 4, 5, 6, 7, 8 spaces away from the right. And so again, and it would be a positive exponent because it is very, very big, and I would want to take a small number and multiply by a bunch of tens to get that big of a number. And you might be wondering, do I have to write it as 3.0 or what? But no, of course, because 3 is a whole number. You could just write that as straight 3 times 10 to the 8th, and that's fine as well. Since, again, that leading number is between 1 and 10, we are fine either way. And that would be approximately the speed of light. Now, if we wanted to use that, say in distance equal rate times time, it's going to be easier to work with that number. Another example, your professor has been alive for about 856 million seconds. And actually, I made this particular example a few years ago, so I've been alive for many, many more seconds since then. But if you think about time, like say I'm 32 years old, it doesn't really seem like I'm that old because 32, it's like, what am I comparing it to? But if you actually think about how many days have you been alive, you would have to take how many years you've been alive and multiply by 365. And that starts to become a really big number. Then if you take, well, how many hours of the day multiplied by how many seconds or how many minutes are in an hour and how many seconds are in a minute, you get a really, really big amount of time. And basically it becomes a little bit more sensible. Literally how many seconds have I been alive? Anyways, in the same way, notice it's in the exact same scale as the speed at which light travels. It's actually in the 100 millions. And because of that, I can transition it to scientific notation a lot faster. And when I write numbers with commas, it's a lot faster of a transition if I kind of already know, well, how big is that number? It's really all about the biggest digit in that number. If it's in the 100 millions, that's always going to be times 10 to the 8th. If it's in the millions, that's just times 10 to the 6th. And so you can kind of transition it without actually having to count. And I want to make sure I'm using all of the non-zero numbers because I don't want to round them off. You might be wondering, should I round them off? You can, but if I want to express the exact number exactly the same, you don't want to round off anything, that's not zero. In the last example, it says the length of a short X-ray is around 0.000000007 centimeters. And if you think about a centimeter, that's 100th of a meter, which is pretty small to begin with. I don't have a ruler on me, but if you think about an X-ray and how long that wavelength is, it makes a centimeter look big because it's very, 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 very small fraction of a centimeter big. So short we couldn't even see it. And obviously, if it's a wave, you might not be able to see it to begin with. But anyways, again, if we wanted to write that in scientific notation and do calculations, do math with that, a lot more convenient in there. And again, we want to put the decimal place to the right of the first non-zero digit. So you don't want to do this as 0.7 because that's not between 1 and 10. This would actually be 7 times 10 to the negative. And that would be 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces over. 7 times 10 to the negative 9th centimeters in length. And the last thing I wanted to mention is, well, what if we wanted to do exactly the opposite? What if we wanted to take a number in scientific notation and change it back to decimal notation? And decimal notation is just another way we say the normal way we write numbers. So that might trip you up because, well, what does that mean? What if it does, like, this doesn't have a decimal, but it's technically in decimal form. But basically, just put it back. And it's exactly the same thing. I mean, you could just type it into a calculator, but some of these numbers are too big even for your calculator to handle. Actually, no, that's not true, and I'll show you what I mean in a second. But if I wanted to it would basically be undoing everything I was just doing. Basically, I would put this many zeros at the end. And technically, it's not as simple as just adding that many zeros, because really what I want to do is if I'm multiplying by 10 to the 15th, I want to move this decimal place 15 spaces to the right. And if I think about that, well, that would be one space would put it at 62, and then I would have to do 14 more spaces. So really it would be 62 with 14 zeros at the end. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And again, the commas are very helpful with really, really big numbers, just so I can tell. But that would be, you know, really, really big number. Cool. And then with 10 to the minus 5, same deal. We want to take this and move it to the left 5 spaces. And again, one of those would get absorbed by the 3 there. So that would really only have 4 zeros. And I've heard a lot of students, you know, say you need to move it this many, you need to have this many zeros. But if you see what I mean, it's not exactly that many zeros. It depends on how many decimals you have as well. How many decimals are in the front or how many decimals are at the back. Anyways, that will wrap up this video on scientific notation. I know this got a little bit longer than I intended, but, you know, wanted to go through the different ways to change forms.